Hello everyone, I am Abhik Pramanik. I am currently studying in Jadavpur University in Electrical Engineering. Today we will be discussing about the project of determining Boston house prices using machine learning algorithms. So Boston house prices, in this project we will be determining the prices of certain houses in certain locations in Boston city. Now each of these locations are characterized by certain features which is given as 13 attributes in the data set. As you can see here, these are the 13 attributes. So such as per capita crime rate, proportion of residential land, and so on. All of these 13 features describe a location. Depending on all these features, the prices of the houses are fixed. So we have to determine we have to devise a model by which we can predict the house prices. Starting with that, we will be importing certain libraries which will help us to in this purpose. So first one is NumPy. Now NumPy is a Python library that has tools for handling certain complex mathematical calculations such as matrix multiplications, vector multiplications. We do not have to use any type of for loop or while loop. Just it has those tools for doing that for us. Now second is Pandas. Pandas is an excellent library that contains tools for handling datasets easily and fluently. It produces some data frames, and we can use various queries to get the information from the data. Then we are coming to sklearn. Now sklearn is nothing but scikit-learn. Now scikit-learn is a Python library that specializes tools for machine learning only. Our Boston house dataset, house prices dataset, is loaded in this sklearn dataset, so we have imported this. Second is train test split. Now train test split is a function that splits the entire dataset into training dataset and a testing dataset in some radio. Now training dataset is required because during training the model we need certain amount of data to train the model, and certain amount of data is reserved to test the model for its performance. Now these testing dataset are completely unseen, and this has to be taken care of. This has to be unseen during training of the model, otherwise the model will fail. If the error on the testing datasets are low, then we can say that the performance is good and we can accept that model. Otherwise we have to devise a new model. So that's why we have used the train test split. Third is min-max scalar. Now min-max scalar is required for normalization of the data. Now the data, as we will see later, that the data are completely different ranges, so we have to bring them in a common range so that they can be made comparable. That's why normalization is done. Normalization brings all the data in the range of 0 to 1, so they become comparable. And last is mean squared error. Now mean squared error is the performance statistic that shows us how much the model is good or bad. Then we are importing the matplotlib. Now matplotlib has tools for plotting and animation purposes. Now pyplot, this matplotlib.pyplot has tools for plotting line graphs, bar graphs, scatter plots, etc. And animation is used for producing animations. We will use this to show the learning mechanism, and HTML, this is used for display purposes only. So let's start. Now the Boston dataset is stored in a Boston. Now this is the description, boston.descr. This is attribute of the Boston dataset as loaded in the sklearn. So this gives a preview of the entire dataset, the parameters, the number of instances. It is shown as 506, and 13 numeric or categorical data, and one target value, which is the price, obviously. So we are extracting the labels, which are the feature names. The labels are these attribute names, and we are producing a data frame object called features, which will contain the entire data. We can see these features like this. This is the features. Now this is the data frame object. We can see the entire 506 rows. That means 506 instances of data, and there are 13 columns. So these are the data points. And now if we want to see the targets or the prices that we are targeting, so these are the targets, these are the required prices. They're not required, but these are set prices of the data set. So far so good. Our data has come into our, we have loaded the data successfully. So now let's start with manipulating the data. So first we have determined the correlation. Now why correlation? Now correlation is a quantity that shows the dependence of the output with the features. A feature that affects the output, that means the output changes as the feature changes. So that feature will have high correlation with the output, unlike the one that has lower correlation value, that will affect much less, that will affect the output much less. So we have a built-in function in the data frame object pandas called core. So we will use this for correlation, for finding the correlation of the features and the output. And Pearson is nothing but the Pearson correlation coefficient. This can be found out in the statistics and probability. So we are not getting much into this. So now we have found out the correlation. Now this is not in the display. This is not in the displayable form. So we have to produce this. We have to manipulate the. We have to manipulate this in such a way so that it can be displayed properly in a human readable form. That's why we have used this. So we are producing a list of pairs of correlations, that is core of ATTR. ATTR is nothing but the list of all features. So this is producing a groups of or pairs of correlation or correlation value. So this produces a list of all the correlation values basically. Now the zip function produces the pairs of the list pairs. That is, the work of the zip function is like this. If we have two list like this, A, B, C, and another is say X, Y, Z, then zip of these two produces this type of list, that A comma X and B comma Y and C comma Z. So not the zip, but a list of the zip function. This actually creates this type of listing. So we are L is such type the list of all the pairs. Now why this is required? Because we need to sort the features and the correlation values. So in the next step we are sorting them depending on the correlation values. This lambda is nothing but a short term function. So x0 is nothing but the correlation value. Depending on the correlation value, the sorting is is happening. And now, as we have zipped the two lists into pairs, into list of pairs, we now have to unzip the values to produce the two lists again. So this function, this zip again, produces the unzipped values. So that means we are getting two list. One is the correlation list, which is sorted obviously, and the corresponding labels of those correlations. Now we just have to plot them to get the bar graph. So this one is our bar graph. Now as you can see that the correlation values are decreasing, and the highest correlation value is for the LSTAT. Now LSTAT is the percentage now LSTAT is the percentage of lower status in the population of that area, and the second one is the RM, or the number of rooms per dwelling. Now these two features affect the outputs very high, so that's why they have the highest correlations. After that everything goes down. So since LSTAT has the highest correlation, we will start working with LSTAT only. So that's why we have taken the numpy array, this df stat, this dot values, this returns a numpy array effectively. So we have the x data as the LSTAT values and the y data as the target values. So now our task will be to normalize the data. Now we have loaded the min max scaler. The min max scaler scales the data between 0 to 1. So this normalizes the entire data. We have to reshape the data because x is not a vector. Vector is essentially a column matrix, but x is a row matrix. So that's why we have to reshape it into a column matrix, because this min max scaler only operates on a column matrix only. So we have to create it as a column matrix. Now our program will not work on column matrix. We have to use row matrix. That's why again we have done this to convert the column matrix into row matrix. So this produces the normalized data. As you can see, okay, so if you want to see the normalized x values, this is it. These are all normalized. As you can see, these are all normalized, and similarly the y values or the target values, these are also within the range of 0 to 1. If you want to check, these are the target values before normalization. 24, 21.6, these are all these are the target values, and after normalization these are in the range of 0 to 1. Alright, so our data is normalized now. Now we have to split the data into training data set and testing data sets. Now usually the ratio varies from 75%, 15%, then 80-20, or 95-15 and 95-5, and we can use anything as our higher number of training data set means higher computing overload. So we have used 80% of data for the training data set and 20% for the testing one. So the test size equals to 0.2. This is the ratio. This gives the factor to the train test split. So we can check this, that xtrain dot size 404, and 102. Obviously this is 80% and 20%. All right, so we have our testing data set, training data set, all normalized with the highest correlation value x, that is the L stat. So now we can start building our model. Now for building our model, we will be using this linear regression. Now linear regression works on gradient descent. Now what is gradient descent? Now in gradient descent, with each iteration our algorithm will try to reduce the error and thus build a line, so that this line lie in the maximum likelihood of the not maximum likelihood, passes through the maximum number of points in the data. So this is the linear regression. So our model will try to learn some values of m and x basically to learn the model. We just have to manipulate this m and c. M is the slope and c is the intercept of the line. We have to just build that line. So thus we need three functions. One is error, that will compute the error in each iteration. We have used mean square error to find this is the best or the L2 norm error. This is also known as L2 norm error. Then the update function, depending on that error, it will update the m and c values with each iteration. And the gradient descent, this is the main algorithm which uses that error and update function. Now let's see the gradient descent. Now gradient descent, we will be passing some initial m, initial c. The x is the training data set features, and t are the target. Alpha is the learning rate. Now with each iteration, how much the m and c will change, this is controlled by alpha. So alpha is the learning rate. Higher is the alpha, our model will never reach the global minima. Gradient descent means we are trying to reach the global minima, or the optima, or the optimum point. Now if alpha is very high, then it will never reach that optimum point. It will keep on oscillating around the optimum point. Too low the alpha, that means our computing time will be very high. So that's why we have to make a judicious choice for this alpha. Now, echoes are the number of iterations that we need to do. Error threshold, this is the error threshold. This marks the error below which we can break the operation. That means we can take that our model has trained enough. So now this alpha equals error threshold, and the initial m and c values, these are called hyperparameters. Now hyperparameters are certain are those values which are given by the trainer itself, or the developer itself, so as to build the model properly. This is not learned by the machine. Parameters are the ones, those are learned by the machine. Essentially the m and c values are the ones are the parameters of the model. These are the two values which are being learned by the machine. So we have devised an error list which will store all the errors with each iteration, and the MC values list which will also store the MC values, m and c values with each iterations. So starting with the iteration, we are first of all we are finding the error. So we have the error, and second we are using the second, we are using the condition that if E is less than error threshold, then error threshold has been reached and we can stop the learning. That means we are setting the break and returning from the function. Otherwise, we can append the error into the list and update the NC values. Now once the values is updated in this iteration, in the next iteration the error will decrease. Our algorithm will try to decrease this error. Once the error is decreased, our machine will stop the learning. Otherwise it will stop here or stop when equals has been reached. So here our mechanism, our learning is starting. So this time, this is a magic function. In Python, this magic function is used to determine that how much time has been used, how much computing time has been used for learning our model. We can see this. So we have taken an initial m of 0.9, initial c of 0.0. Now these initial values are very important in some of the models. Not in this model, this is not so important, because this is a convex, perfectly convex data set. That's why that's why the whatever initial value we will take, it will reach the optimum value. But say there is a local minimum, in that case we have to make a judicious choice of the initial values. Otherwise it may happen that our algorithm will reach a local minima and say that it is the most optimum point, whereas the global minima is the optimum point. So that's why initial values are not so important in all problems, but in certain problems this is much important. This has some importance. Then we are coming to the alpha, which is the learning rate. 0. We are taking here it to be 0.001 equals as 400. Now this can be taken as 250 or much less also, but we are taking it 400 to ensure much more greater learning. Now, and error threshold is 0.001. So this is the gradient descent, and and here we can see that the CPU times, how much amount of time it has taken. Now this plot function, as we have seen the matplotlib, the plot function, this plots the error. As you can see here, it has used 400 iterations, and the error has started from 0.07, it has dropped until 0.01, and then it seems like it is almost constant, but it is decreasing slightly. So this should be the nature of the error curve. Always the error should decrease, and that's why this is also known as the gradient descent. That means we are going downhill such that the error keeps on decreasing. So that's why this is a gradient descent. And so we have scaled the error also so as to fit in the animation properly. Now we are going into the part for animating our regression line. This will show how our model is getting trained with every iterations. Now for this we are using the func animation function. The func animation is actually a constructor. It produces an object, an animation or an animator object. It takes these parameters, this is the figure on which the animation will occur. Update frame is the frame update. This is a function, and we can pass function as values in Python. This is possible with Python because Python is entirely functional program, supports functional programming. So update frame is a function that computes the frame in every update, and these are the number of frames. Init function is the initialization function. This is the initial frame from which our animation will start. And blit, if we put the blit true, this produces a much smoother animation. Now okay, so we have to define the data now. So we have taken MC values and anim as a separate list for the animation values. Now here we have used only 40 values. This can be taken as 400 values, but in that case the CPU overload will be very high. So depending on the CPU we can devise it, but we have taken only 40 values for our first only 40 range value for the animation. Now the PL subplots produces two subplots. As you can see here, these are the two subplots. One is for storing the error, another for the regression line. In both cases we will see how the model is getting trained, and thus we are creating two line objects, one for one axis, that is now the subplots return two objects. One is the fig, another is the one is the figure object, the entire figure, which is this, corresponds to this. Another is the axis. Now the axis means these axis objects. This actually shows the plotting areas. So this is the AX object or the axis object, and depending on the axis object we can plot the empty fields and keep on updating with each update like this. So here is our animation. We can I will just start it from the start. So here is the animation. As you can see here, that the line is starting something like this, and our data points are the green points. Those are all the training data points. And now our error is at the highest, that is at 1. Now as the training goes on, the error is decreasing and our line is starting to align with the data point. So as this goes on, the error is now has reached a threshold, not threshold, but is at the minimum value. And as you can see, the line has almost aligned with the data. It is almost passing through the maximum of the point. So now we can say that the model has been trained. So thus we can say that our model has been trained properly. Now as our model has been trained, we are happy with our model being trained. Now we have to test our model on the testing data set. That means we have to devise the performance of the model. So we have used the predicted. We have produced another list called predicted, which stores the predicted values of the X test features. Now this is essentially a matrix multiplication, but this is done by Python entirely because of the NumPy module we have imported. And now the mean squared error of the Y test are the true values and the predicted are the predicted ones according to our model. Now we can see the MSE here like this. Here is the MSE. Now as you can see, the MSE is quite low, 0.017, and if we just produce a scatter plot, this is the scatter plot of the testing data and our model line. This is model line, then this is the scatter data. Now the data here is in the normalized form. This is of no use. This cannot be used in any case, so we have to revert it back to its original form. So that's why we have to use inverse transform of the min max scalar and produce the true results. Now the true results are produced and another data frame object has been produced to see the values. Now as you can see, the true values and the predicted values are almost near, though some of the outliers are there which are varying much, but then also they are almost near to each other. So we can say that our model is almost near to accurate. Now this is for LSTAT. We can do the same for RM, that is the room per dwelling. So we can only just change this value and give this. These are the Y. This is the training time, as you can see, 53.2 milliseconds, and the error now becomes like this. This is the error, and you have to give some time. Now this is the, we can see how the model is getting trained. This is the initial line. As the training is going through, it is aligning with the data and finally gets aligned. The error is quite low now. So if you see the predicted values and MSE, now the MSE has increased. This means that the LSTAT values are predicting the outputs much more accurately than with this one. So this is the scattered and the model. Now see, this is the predicted targets and the true targets, as you can see here. Alright, now this is for RM. This is the second highest coefficient correlation value. Now let's see what happens if we use a very low feature which has a very low correlation value, like this CHAS, or CHAS means Charles River dummy variable. Alright, so if we use this, this is the prediction value. As you can see, the errors will be quite high. This will be quite high, very high. This will be very high. Now predicted the MSA value, as you can see, it's 0.035, almost quite 2 times of the value as we are of the MSE value as we are getting with the predicted values, with the predicted value with the LSTAT feature. So we can say that as the correlation value decreases, the performance of the model also keeps on reducing. As you can see here, this is the data and these are the predicted values. some of them are matching, though some of them are varying too much high. No, this is not a good model. This is not that a good model. So now we can say that the performance of the model greatly depends on the type of feature, the correlation of the feature with the output, the amount of training data set, and the type of learning algorithm we are using. Now here we have used the linear regression for building a model. We can even use ANN for building a model. In that case, the regression line will be a non-linear one, and thus the error will be much less. It will be much less. Here, as you can see here, that this cannot be shown as one line. This has to be shown as two lines. If there are two lines, then the output will be much more accurate. So that's why we need to we can use different type of learning algorithms to build a model properly and efficiently. So this ends up our project discussion, and we can say that the highest performance of the model is achieved when LSTAT feature is used, and the lowest one with the CHAS. It is linearly varying with our correlation, with the correlation values, that is the correlation with the target values. Thank you.